All right, guys, last Navier Stokes problem. This one's for a fluid contained between two infinite inclined parallel plates that form an angle theta with respect to the horizon. Plates are spaced at a distance h, and the width of the plates is w. And both of the plates are fixed. They're not moving, zero velocity. Using the conservation of momentum and the Navier Stokes equations, we need to find the volumetric flow rate for the fluid. We assume fully laminar developed conditions, constant fluid properties, and steady state. So let's go ahead and get started. All right, guys, inclined plates, find the velocity profile and then the flow rate. Pretty easy problem, but in this case, nothing's different. So if you've been following the other videos, you'll know that we always start off with the Navier Stokes problem, right? The equation, I'm sorry. I tilted my axis. It's better to tilt it. I explained in the previous video, but it's better to tilt it because if you were to have the normal x and y, now you'd have to use both the x and y component of this Navier Stokes equations, okay? If you were to tilt it, the only thing that changes is you have to deal with a g, like theta version of the g, okay? And you'll see what I mean in a second, but it's better to tilt it now, and then you just deal with the x component, right? So it's at a height h. It's tilted at an angle, fluid's in the positive x direction. There's nothing going on in the up and down direction. You have two infinite parallel plates going into the plate. The x component, right, for the Navier Stokes equation in Cartesian form is just this. And this is what I like to use. I just like to divide density to everything. So this will get a -1 over density, right? That row cancels out with this row, so you'll just get g of x, and that mu, because of this relationship, will turn into nu, okay? So if we do that, this is what we get, okay? Now, we have to start canceling out the terms. This is easy. If you watch the previous videos, you know what I'm talking about, but I'll go ahead and do it one last time for you guys right here. It's steady state, so this term goes away, right? Flow is only in the x and y and it's only in the x direction, so y and z velocity profiles are 0, okay? So this term goes away and this term goes away, boom, boom. And this term went away, boom. So that means we're left with this term on this side. It's a 2D problem, okay? So that means going into the paper, you're not gonna have any change in what your profile of velocity looks like. In this case, I didn't draw it, so I'm just gonna go ahead and show you a different problem that I just did. But in this profile, look, this is what I mean. This is what the velocity profile looked like. That I think, I mean, you don't have to think. I mean, I'm just trying to explain to you what I'm trying to say. Going into the paper, it's going to be the same. So this triangle shape is going to be the same here, here, here. It doesn't matter how deep you go into it, it's going to be the same profile. And that's what that's trying to say, okay? So because of that, the partial u over partial z is 0. So take the derivative of that, then you're just going to get another 0, okay? That's what that means. Watch the previous videos if you don't understand. It's in the first couple minutes. You won't waste so much time. So just like that, I canceled this term out, all right? Conservation of mass for an incompressible fluid tells me that partial u over partial x plus partial v over partial y plus partial w over partial z is equal to 0. The change in velocity in the x direction with respect to x plus the change in velocity with respect to change in velocity in the y direction with respect to y plus change in velocity in the z direction with respect to z is 0. Well, we already determined that there is no flow in the y or the z. So take the partial of this with respect to anything, you're just going to get 0, right? So 0 and 0. So that means this is equal to 0, okay? And that's what I kind of wrote here, okay? So once I know that's 0, well, that's just this right here. Partial squared u over partial x squared 0, right? Take another derivative, and that's 0. So just like that, this term got canceled out. And so everything here is 0. And then this term got canceled out. So now these two are 0. So now I'm just left with this one. And these two right here, okay? So let's look at the gx, okay, right? So pretend this was my original xy, right? Positive y, positive x. It tilted this way, right? That angle theta. So it went from here, look at the red pencil. It's going to create an angle theta with respect to the original y-axis. So this angle right here is theta. That means this angle here is theta, right? Draw a straight line down my pencils. And to the left of that straight line, that angle's theta. And that's what I did here. So to get the x component, right, where we care about this one, direction of the fluid. So we want this one right here, going g of x, right? G of x is also right here. So we want g sine theta. That's how we get that. Okay, so just like that, I have g sine theta. There's a pressure that exists that's flowing the fluid, right? So just like that, we have this as our Navier Stokes equation. Is g sine theta, g of x, minus 1 over density, delta p over delta x, right? The pressure in the x direction that's moving the flow, because both plates are fixed. So in order for the plate to move, there has to be a pressure. It has to be like something pushing the fluid. And that's what that means, okay? Plus this term. Boom, this times this. And I put the substitution back in, the one I got from here, right? When I divided by density to both sides. So I just went ahead and did that substitution, nothing crazy. And then I isolated this right here. Okay, that's the main goal. You want to isolate this second order differential equation, and then you'll have this, okay? I mean, it's just basic algebra that I did. So I'm left with this. Now that I have that, I could go ahead and integrate this twice to get my general solution, okay? And let me show you this right here. So when I did that, this is what I'm dealing with. Integrate this with respect to y, that becomes a y over mu, and then plus c1, okay? And then integrate it one more time to get the velocity profile general solution. It's just y squared over 2 mu plus c1y plus c2, okay? So now that I have that, I need boundary conditions, because I need 2 of them because I have c1 and c2, right? So 2 boundary conditions, let's see what they are. I'm right here. So in this case, this is where you got to think a little intuitively. This is where the engineering mind comes in. You got to know, kind of predict how the flow is going to happen, okay? The 2 plates are fixed. We know because of no slip condition that velocity at this plate is 0 and this one's 0. So I think the flow is going to look like that. It's 0 at the top and bottom and very high in the center, okay? That's what I think is going to look like. And in this case, I chose my datum line because it goes from 0 to h, right? That's what the problem told us. So y is equal to 0, h over 2, and then h, okay? You could have done y is equal to 0 at the middle, and then h over 2 up top, h over 2 at the bottom. As crazy as it sounds, it wouldn't change your answers at the end. It would change your velocity profile, but at the end of the day, when you start plugging in any h values for y, it shouldn't matter, because that's the whole point of, right? The whole point of Navier Stokes, guys, is to find the velocity profile of a fluid, okay? That's what you need to understand. I know you guys are in it just to get the A in class, but you really need to understand that. It's to obtain the velocity profile and the pressure of a fluid, okay? That's what we use these equations for, just FYI. In this case, my datum is from 0, h over 2, and h. So I could do 3 boundary conditions if I wanted to, but I just need 2. So what a lot of people would do is just, hey, the velocity is 0 at point number 1 right here, and velocity 0 at point number 2. I did a little differently just to kind of, if you guys are curious, right? It's very easy to do these 2, but I went the extra step for you guys in case you're curious how you do this one right here. So I put at y is equal to 0, my velocity is 0. So when I do that, you set u equals 0. So this becomes a 0, and for every y that I see, I'm going to plug in 0. So that's 0. So all this goes away. C1y is 0, right? So y is 0, so that goes away. So that means C2 is 0. Now, again, I could have done the other one. Let me go ahead and do it real quick. So at point number 2, velocity 0, okay? So I would have used this equation, 0 is equal to, and for every y that I see, I'll plug in an h. So I'll get h squared over 2 mu times all this plus C1h plus C2. And then I already found out C2 was 0, so just solve for C1 in that case. And boom, you're good. What I did was I got this term, and I knew that the change in velocity with respect to y was 0 at the very center, right? Because look, take the derivative, that's just like that, straight line. And that's a 0 slope. So what that means is I'll get this equation. I know this, like I just told you guys, right? At the very center, the change in velocity is 0. So this is 0. And then for every y that I see, I'm going to put in an h over 2. That's what I did. I put h over 2 mu times all this plus c1. And look, it kind of looks similar, right? Because remember I told you guys you get h squared over 2 mu plus c1y h. Well, this was equal to 0, so take out an h from both terms, and you get exactly this, h over 2 mu times all this plus c1. So it would have worked, right? But just FYI, that's how you do this one. In that case, just found c1 and c2, right? Just solve for c1, c2 was 0, and now we have a particular solution. So now we get this velocity profile, plug in c1 and c2 that we just found, and that is your particular solution, okay? And that's just algebra at this point. Just plug it in. It's nothing crazy. So boom, just like that, that is my velocity profile. Now the answer, the problem is asking to find the flow rate. So the flow rate, I'm gonna show you guys the answer now. The flow rate, we know from fluid mechanics early in the course, that is just cross-sectional area times velocity, okay? Average velocity. This is not average velocity. This is a velocity profile. This tells you anywhere along the y direction, up and down, how your velocity is going to be. It's going to be max at the center. It's going to be 0. And it is going to be 0, right? Go ahead and plug in 0 for every y that you see here. So we know C2 0, and this is our formula right here. We already did it actually. Plug in y equals 0, your velocity should be 0. 0, 0, this becomes 0 times all this, velocity 0. That's confirmed. Now plug in h, that should also be 0. Y squared becomes h squared minus, that's a y, that becomes an h. H squared minus h squared over 2 mu, that's just 0. Multiply to this, velocity 0. Cool, that makes sense. That's exactly what this tells you, right? That's the whole point of Navier Stokes. It tells you the velocity profile. So this isn't average velocity, my bad, I got sidetracked. This isn't velocity, this is a velocity profile, not average velocity. So we need the average velocity. So what's the average velocity? So how do you get the average? You just get the integral, right? This is a curve. We want the area under the curve. Because the velocity is high here, it's 0 here, it's 0 here, it's symmetrical, but where is the average? So it's easy. All you do is take the integral, and then you divide it by your total height. So that's what I do here. I take the integral with respect to y, and you divide it by your total distance. In this case, that distance is h, 0 to h, right? So this divided by h, and then times area. Width times height. So this is what we're looking at here, and then into the paper here, okay? So this h, total distance, is going to cross out with that h. So at the end of the day, you're just going to multiply by width. So that's what I have here. Q dot is equal to w times the integral of velocity. When you do the integral of velocity, you get this function here, and you plug it in. In this case, the only things that get integrated are these two terms. I factored out everything else, right? That 2 mu got factored out, and this got factored out. You integrate it from 0 to h, so you're not going to have a constant, plus c1 or whatever. And yeah, at the end of the day, it's just basic integration. Y squared, y cubed over 3, minus y squared over 2h, and then from 0 to h. Evaluate it, do math, just look at it, and that's your flow rate, okay? If you wanted to do it per unit width, get rid of the w, right? Because you divide by w, so you just get rid of the w. And that's it. Very easy. This is the last one for Cartesian coordinates. I hope that helped. There's 8 problems, 8 videos. If you know how to do all 8 of them, I guarantee you will be a pro for Navier Stokes on your exams, I promise. So yeah, just dedicate some time to it, look at it, make sure you got it, and I hope that helped.